In the next, we will move into the realm of backpropagation. The business of backpropagation is to calculate in reverse order how to change the model parameters so the loss reduces, or the loss changes to the direction where we would like it to change. Well, we start, of course, from the loss function. And the first task is to make clear of how the final output, that is the prediction of the model, look, the prediction returns this, give the prediction here, and the prediction is then fed into the loss function. How to change this prediction so that the loss function change. And after make clear of this part, we'll be able to consider how the, if you recall, when we derive the gradient in the backpropagation discussion, we will have how y change will affect how the loss function change, and from this starting point, we will start the backpropagation to calculate the gradient of all parameters in the network. So in this video, we will calculate the gradient of the final output of the model, the gradient of the loss function with respect to the final output of the model. Let's consider the equation. It's simple enough. Y is a constant. This is constant as well. So if you recall the derivative of log something with respect to x, the input of the log is just 1 over the quantity. So if we substitute this relationship into this, we'll have consider one particular prediction at sample I for now. Then we do not need to worry about this summing over, because the samples are independent with each other, so the prediction of sample I only affect the particular item calculated at the sample I. So therefore, we have yi times, remember the factor of a function, when a constant factor of a function will join as also as a constant factor as a derivation of the function as well. So this is 1 over pi, and for this part it's simple enough as well. 1 minus yi. This is 1 minus 1 minus pi. Do not forget that we have a negative in front of pi, so we have another derivation factor according to the chain rule. Okay. So to be specific, the log 1 minus pi is d log 1 minus pi d1 minus pi times d1 minus pi dpi. So this is 1 over minus pi, and this is negative 1. Remove this part and take a note of this. We will implement this equation. Okay, let us write it here. That's the loss y gradient with respect to the prediction. This sample, this is not a good habit to write comments. You can do it here. So we just need to return y over prediction minus 1 minus y over y minus prediction. Do not forget this negate. And because we take a mean here, that means each item in this summation contributes with a weight of 1 over the number of samples. So that calculates the derivative, the gradient of the loss function with respect to the prediction. Let's test that. Unlike the loss function itself, the derivative, the gradient of the loss function with respect to prediction will have the size same as the prediction, because we want to find out how each individual prediction affects the loss function. Print d loss prediction. Okay, that's this number. But of course, you may ask, look, how would we know those numbers are correct? It's vitally important, because if those numbers are wrong, then everything will be wrong, because we will start from the wrong starting point when we perform the backpropagation. A good practice to do this backpropagation, to this kind of calculation, is to introduce a unit test at each step. So I'd like to test the derivatives using a numerical way. How? Okay, let's define a test function of d loss numerically with exactly the same function signature. That means the input parameters, the input arguments of prediction and y. What we want to do is we want to change each individual element of the prediction a little bit and investigate how that would affect the value of the loss function. And then later we will compare this numerically by numerically disturbing the computation and this numerically computed gradient with the analytically computed gradient. So now let us have a variable to sieve the numerical gradient. That would be the, we started with numpy gives a function of allocated array that are all zero, all elements are zero, but with a shape like another array. That is exactly what we want. Then we will do a for loop. We will for loop over all the n elements. Well, we will set n to be the prediction size, and we will perturb the element of the prediction a little bit. But note that the derivation here depends on the prediction itself, and therefore after we have disturbed it, we want to revert it back to the original value before we disturb the next element. So we need to allocate to save that the original value, prediction I, and then we will disturb prediction I. Let us allocate some very small value. For example, 10 to the power of -6, that is 1 millionth. And using this new value, we will consider the change in the loss function. That is the loss, the perturbed prediction, and the y loss 0. Of course, we need to compute the loss 0 before. this loss 0 is the loss without any disturbance of the prediction. Okay. And how the loss has changed with respect to the disturbance, that is the epsilon. And lastly, let's revert the perturbed array of prediction back to its original value, P0. And let us return the so computed gradient, numerical gradient. Hopefully this works. Let's run this part. Fine. Let's also print the loss numerical and the prediction and the y trim. Okay. Well, I think we need to I think we need to scale that by n. No. In each set we only disturb one sample from this. They are pretty the same. So look at the first one, 0.027 minus 0.029. So let's check the difference. Minus the loss numerical prediction y trim. Okay. We have seemed to arrive the correct implementation of deriving the loss function with respect to the output of the model. The difference between the numerical evaluation and the analytical result is very small. They are in the order of the magnitude is in the order of 10 to the power of -8. That's approximately 100 millionth